Well, hello again. You guys have got to be getting sick of this already, and this is lesson number 2. But here we go. The good news is we don't have a lot more to get through before we basically wrap up this curriculum and move on to review. So anyway, here we go. So yesterday you watched the video on finding the volume of a solid if we rotated a curve around the x-axis. Well, now we're going to rotate, instead of rotating this way, we're going to be asked to rotate things around the y-axis. Not a whole lot changes, but enough changes to make it annoying. So let's go through this first example. Rotate the area enclosed by the curves. Y equals the square root of x, looks like this. Y equals 2, looks like this. And x equals 0, looks like this. So they're asking us to rotate this around the y-axis. So we're not coming down. If I did come down and I had a shape like this, I would revolve this way and I'd have that washer method. I'd have a big hole on the inside. But that's not what they're asking me to do. This time they're asking me to go around the y-axis. So this way. So if I'm going to draw the mirror image, I'm going to draw it like that. Look, it's a totally different shape. I don't have any hole in the middle. This is a solid. I don't have a hole to take out. I had these circles going around this way, and they're all filled in all the way. So the idea is still the same. We're still going to be finding the volume by doing pi r squared minus pi r squared, r being the radius of the outer circle, and this r being the radius of the inner circle. So the concept is still the same, but what's different is that these circles, instead of being stacked this way and adding up the area of a bunch of circles this way, they're stacked horizontally, and I'm stacking them up. So two things change. The first thing that changes is, instead of going from x to x, and I'm adding up the circles that go this way from x to x, I'm going this way, so I'm going from y to y. I'm going to add up the area of all the circles as I stack them on top of each other, bottom to top. So the limits of integration are going to change. I'm not going to use x's anymore. I'm going to use y's. So you're going to be using your bottom y and your top y. So when I find this point of intersection, I really don't care where I am on the x. I care where I am on the y. So when I made this shape in the first place, this was the square root of x, and this was y equals 2. So that's how high up I'm going. So I am going to already set up my integral and know that I'm going to go from a y value of 2, from a y value of 0 up to a y value of 2. I'm also going to have pi r squared, but now I'm going to be with respect to y. It won't matter when you put it in your calculator. You can use y's or you can use x's, but I am, when I write it, thinking about this being with respect to y. So this is still my radius. I don't have 2 because, again, I don't have something to cut out or leave out of the middle. This is solid all the way through. But the difference here is the radius that I use cannot be in terms of x. I can't go throw the square root of x in here because I'm not using x's, I'm using y's. So I have to take that curve, y equals the square root of x, and I have to solve this for x so I can use it in terms of y. So I'm going to take this curve. I know that this is what the outer circle's radius is, right? If my circles are made this way, the radius of each circle comes out to this square root curve. But instead of using y equals the square root of x, I'm going to square both sides here. And I know that x is going to equal y squared. I'm going to use y squared as my radius instead of the square root of x. It's the same thing. I'm just taking this curve and I'm solving it for x so that I can plug in something in terms of y into my formula to use. So this is the setup. It's really not different. It's just, well, it is different, but instead of my circles being stacked left to right, they're being stacked bottom to top. So everything has to switch and be in terms of y instead. So this is still the integral from 0 to 2 of pi times y to the 4th dy. When you put this in your calculator, actually we could totally do that by hand easily, but whatever. So if I put this in, If you want to use y's, that's fine. So y to the 4th, but then you got to make sure you go dy over here, and I didn't put in pi. Oops. So there we go, and I get 20.106. So the concept's not new, but the way we have to like actually do it is a little bit new. So let's try the second one. Example 2, find the volume found by rotating the area between the functions y equals root x and y equals x around the y-axis. So maybe pause the video, see if you can draw it, and if you draw the same thing I draw. But we've got the square root of x. And you know what? I'm not, which one's on top of the other? The square root of x like this? I would imagine so, right? If you're not sure, graph the square root of x, graph y equals x. If you can't really see it, let's change the menu. I'll go standard. There we go. So yep, that square root curve is above the line until a certain point. So we've got this, and we've got this little tiny guy. Might as well get this point of intersection right away. Sometimes I do that before I've done anything else. If you're not sure, that's definitely going to cross at 1, 1. What other point is going to make that work? Nothing. So this section is what we're rotating around the y-axis. So again, I'm not going down, I'm going over. There's the mirror image. I've got an outer circle now, and now I've got an inner circle. So I'm going to have a radius of an outer circle minus a radius of an inner circle. So again, I'm going to integrate from bottom y to top y. Bottom y is 0, top y is 1. And I'm going to have a pi r squared minus a pi r squared with respect to y. So I want to know which my outer one, what's my inner? Well, my outer is definitely my line. So that was y equals x. The inner is my square root curve, y equals root x. But neither can be used in that form. Both need to be solved for x. This one already is. So this is the radius of my outer curve, comes all the way out to here, so that's just y. The radius of my inner curve comes to here. I can't use y equals x, I need to square both sides. X equals y squared. So there's the integral that I'm going to use. Put it in my calculator, get an answer. Okay, now maybe you'd want to pause and try example 3 yourself and then come back. But I'm going to do example 3. So we're going to rotate the area bounded by y equals x squared plus 1. I have a parabola. Y equals 0, that's down here. X equals 0 is this, and x equals 1. So they're talking about this area. So I really don't need the left side of this parabola, although I'm going to draw it in a second when I reflect. But they want this space to rotate around the y-axis. So this space, I'm going to draw its mirror image, come down. And now we got a kind of weird situation going on, and my drawing's kind of terrible, but whatever. Here, things change. Above this point, I have an outer circle and an inner circle. Below this point, I have only an outer circle. So I'm going to actually need 2 separate integrals. Aren't you glad you got up today? So let's talk about the bottom part first. So this bottom part, if I'm going to integrate, is just going to be pi times the radius squared from bottom y to top y. So I'm going to cut myself off here and figure out what y value this is at. Well, we know this is at the y value of 1. So from 0 to 1, I'm integrating the radius of this circle. And the radius of this circle is just 1 the whole time. This radius doesn't change ever. So I don't really need to worry about what variable I'm using because the radius is just 1. Up here, now I have an outer circle and an inner. So I'm going to still have pi, but I'm going to have the one radius squared minus the other radius squared. I'm going to go from the bottom y to the top y. So now I know I'm going to go from 1, but I don't know where these meet. So I'm going to have to figure out where they meet. You could graph it, or we could be cool and say, okay, well, if this is where x is 1, let's plug that into here. So this is going to be a y value of 2. If you don't see what I did, I'll say that again. If I'm trying to figure out where this is, I'm saying, okay, well, if this is x equals 1, and I know this curve is x squared plus 1, I'll just plug 1 into this and get the y value as 2. So my second integral is going from 1 to 2. And now I need pi times the outer radius squared minus pi times the inner radius squared. I took the pi out to the front. The outer radius squared is still 1. I'm sorry, the outer radius is still 1, and the inner radius now is made by this curve. But I can't use this curve as it is. I need to solve this for x, because everything I'm using now is with respect to y. So I'm going to subtract 1 from both sides and take the square root of each side. So the square root of y minus 1 is what I'm using there. All of this can go into your calculator and give you a beautiful answer. Whew. All right, that's only 11 minutes, not too bad. You might want that answer, so I'll get it for you. Actually, oh gosh. Okay, here we go. So pi times from 0 to 1 of 1. I'm going to go to, you can use dx's, you can use whatever you want when you use your calculator as long as you're consistent. So I don't know, my hand just goes to the x. I'm going to put this in, so the square root of that squared is just going to be x minus 1. And obviously I could reduce that, but you know, if I know it's right and I put it in like that, why go back and fix it? So I've got, double check, I've got pi times the integral from 0 to 1 of 1 squared dx plus pi times the integral of 1 squared minus, oh shoot, do you see what I messed up? That should be in parentheses because I am subtracting the whole thing, so I have to be careful there. And I get 4.712. Hopefully you did too. All right, let's do some Khan Academy and we'll do some practice. I hope that you're having a great day.